do this. Very few people here today. Well, let's just get on with this. Now I don't even know if this is the correct lecture number because we've missed a couple of lectures. Technically, we should be lecture 17, but I think we are kind of at lecture 15. But I'll leave it open. So what are we going to do today? And then Friday. So today we're gonna do the more on paper solution of the 2D problem. And then on Friday, we have a Python lecture. So I'll just do the same as today, but in Python. And what we are doing today and Friday, actually today is probably enough to do your homework. You could already try, but from what we do today, then it should be clear what you should do for that third problem of homework 4. So what we have done before, strong form to weak form, we had a week to do that in 2D. Then we have talked a lot about discretization of elements in 2D with either triangular elements with XY shape functions, triangular elements with Saeta functions, and quadrilateral elements with Saeta functions. And then given the interpolation, what we are doing today is this. So we are going to see what happens when you put that interpolation into the weak form to get the system of equations. So reminder of what the weak form is. This is what the FE is solving, is the integral over the domain of the gradient of the shape function times the gradient of T. This D is the conductivity, and it could be a matrix. So this is conductivity matrix. But if it is isotropic, then it's just a number. The reason why the book has a matrix there is because it leaves it open for an isotropic diffusion. So in the lab 4, I think it's lab 4, you did the heat transfer problem, and at some point you did an anisotropic heat transfer problem. So for that one, the D is still diagonal, but it has different diffusivities or conductivities. But for today's class, I'm just gonna use isotropic conductivity. So then no D, just a single constant K. For today, D is just K times the identity, so we can ignore the matrix and just use K, the conductivity. But you know, this is a little bit more general. So that integral equals minus the integral over the boundary with fluxes. Note that this is only over the boundary with fluxes of the weight function times the flux plus an integral over the domain of the weight function times the source term. And that has to be satisfied for all W's that are in the space where they vanish at the boundary. So that's the weak form. And then do I have, yes. And then what are the discretization with shape functions? Remember that we can have for the shape functions for the triangles, and which are, there's the two elements that we were talking about, triangles or quadrilaterals. For the quadrilaterals, we can have shape functions in terms of x, y. And in that case, the function that you interpolate is directly in terms of x, y. So the function is sum of shape functions times nodal values. And then the gradient is just sum of the gradients of the shape functions times the nodal values. So this one works, but there's a but for that. That in general is very difficult to do two things. One, to build these shape functions. For the triangle, it's possible, but that's it. For the quadrilateral, it's very difficult. And then that's one of the buts. And the other one is the integration. So if you are doing your homework 4, I'm asking you to do some integrations that involve the shape functions and the gradient of shape functions in terms of x, y. And you can see that even doing those integrals for a triangle, which is a very simple shape, And I gave you a triangle that has an edge that is aligned with the y-axis. And even in that case, if you want to set up the double integral, it's a little bit problematic. So it's much easier, especially to do the integrals, to work with shape functions in terms of psi eta, just like we did in 1D. So on the one hand, the shape functions in terms of psi eta or psi 1, psi 2 are very easy to define, and they are the same for any element, but it comes at a cost, and the cost is that you need to evaluate now not just the function. So if you want to interpolate the function, you still do sum of shape functions times the nodal values. But now you also need to interpolate the geometry. So you need to interpolate x as sum of the shape functions times the nodal coordinates. You need to interpolate the Jacobian, which is the derivative of the x with respect to psi. This is a 2x2 matrix. And now if you want gradients, you can not take directly gradients with respect to x. You can take gradients with respect to psi. So you need to multiply by the inverse of the Jacobian in order to get gradients with respect to x. So that's what we talked about last time. And then to do integration, we just do the same as for the 1D. There's some table that has the points at which you need to evaluate and the corresponding weight of those points. For quadrilaterals, like I said, it's not possible. I guess it should be possible, but it's very, very difficult to try to get shape functions in terms of x, y. So easy to get shape functions in terms of psi eta. Again, the thing that comes with that is that you need to evaluate the isoperimetric map and the Jacobian. See code from Monday, not from Monday, because I did not get to the code. We'll do this on Friday because I didn't get to do the code. And then similar to the triangles, if you want to interpolate functions, you sum shape functions times nodal values. If you want to get gradients, again, you can easily get gradients with respect to psi, but if you want gradients with respect to x, you need to multiply by the inverse of the Jacobian. So same ideas for the triangles. Any questions up to this point? All right, so let's go ahead and put the discretization into the weak form. So we are going to put that gradient W. So this gradient W is going to be the sum of the gradient of shape function I. Somehow we can get the gradients with respect to x. Again, if this involves multiplying, getting gradients with respect to psi and multiplying by the inverse Jacobian, we can do that. But this will be the gradient with respect to W. Again, sum of the gradients of the shape functions times the nodal values. The gradient of the temperature is sum of the gradients of the shape functions as well times the nodal values. W is going to be just sum of Ni Wi, and that's all we need. There's no temperature appearing. I mean, I can write it, but there's no. This is for an element, because obviously the shape functions and the gradients will change from element to element. So if we plug that into the weak form, then we're gonna get, this equation is no longer gonna be true because I'm only gonna do it per element, but I'm gonna write out what the integrals over an element would look like. So this first integral, when you plug in the discretization, it's gonna look something like this. And then, like I said, I'm gonna ignore the matrix. I'm just gonna put K for the conductivity. And then sum of the gradient of shape function J times Tj d omega e. Then I'm gonna ignore this for now. And then the other integral that we need to worry about is this integral right here. That integral, when I plug in the discretization, is going to be an integral over the domain of sum of, this doesn't have to be a transpose because it's just a scalar. This one, it has a transpose because this is a vector. But, and I wi times s. So again, all I did was put in the discretization into these two integrals. And now what we're gonna do is, okay, good, I have empty. Now we're just gonna do a little bit of algebra. So for this one is gonna give rise to the stiffness matrix. So algebra. These are all operations that are linear. So all I'm gonna do is I'm gonna take the sums out and the nodal values out. And then I'm gonna leave the gradients of shape functions inside of the integral. And the reason why I can take the sums, again, because this is some linear operation, so sums can be factored out. It's kind of like doing, A times B plus C type of thing. So this is the same as AB plus AC. These are linear operations satisfy this. You can split the sum, you can distribute the operator. So I can take the sums out. And then in terms of the taking out of the integral, the nodal values, this Wi and this Tj, they are just numbers. They are not functions. The only things that are functions are the shape functions. The other one are, as the name suggests, nodal values. So I can just take them out. So what I'm gonna end up with is I'm gonna end up with the two sums outside, all the nodal values of the weight functions. And then here, I'm just gonna end up with the gradient of Ni transpose gradient of Nj Tj. Again, just some algebra. And these two sums and this Wi, this Tj, what you should be thinking about is this is a vector matrix vector multiplication. It's just split into this or expressed with these sums, but this is nothing but a vector matrix vector multiplication. So you can rearrange things and put all the nodal values of the W in a vector. And depends on which element you have. If you have a triangle, then you would have only 3 values. If you have a quadrilateral, then you would have 4 values. Last year. Then you have a matrix, which is the stiffness matrix for the element. So this one, by the way, I'm gonna call WE. This one I'm gonna call KE. And then again, I just need the 3 values. E. And what are the entries of this stiffness matrix? Well, they are all the combinations of the integrals of the products of the gradients of the shape functions. By all combinations, I mean, for example, this one is going to be the gradient of the shape function 1 dotted or transpose gradient of shape function 1. The second one, the second entry is going to be the gradient of shape function 1 times the gradient of shape function 2. I'm running out of space. Then the third one is the gradient of shape function 1 with the gradient of the shape function 3. These are symmetric, so I'm just gonna copy that here. I mean, the dot product is symmetric, so I don't need to repeat it. So those are the same. Here, this one is gradient of shape function 2, gradient of shape function 2. And this one is gradient of shape function 2 times gradient of shape function 3. And this one is gradient of shape function 3 times gradient of shape function 3. And this one is just the same as this, because these are symmetric. So that is the stiffness matrix for the heat transfer problem for the triangle. How would it look like for the quadrilateral? Exactly the same, but the W vector would have 4 entries, the T vector will have 4 entries, and the matrix will be a 4x4 because now you have 16 combinations. You will have, you know, N1, 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 N2, N1, N3, N1, N4, N2, N1, N2, 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 N3, N2, N4, and so on. Any questions up to this point? Yes.
Like the integral of the big first integral, what happened to the big T?
Oh, I was saying that the D is a matrix, is the conductivity matrix, but for what I'm doing today, I'm considering isotropic conductivity. So that means K times the identity, and then you can ignore the identity. Because if you have, you know, vector times identity times vector, then it's just gonna be vector dotted with a vector. So you don't need the D. And then the only thing that I left was the scalar conductivity. In the more general case, you would keep the D. But I think for what we're gonna do today and what we're gonna do on Friday, if the D is the identity, well, K times the conductivity times the identity, then you just need to worry about the conductivity. Other questions? All right, so that is the stiffness matrix. I'm gonna do one more thing, which is, I really hope I don't run out of battery. I see that I have 16% left. We'll find out. For the homework and then for how do you actually compute that stiffness matrix? So how to actually compute the stiffness matrix? We're gonna do more of this on Friday. But let's say that you are working with a triangle element. Like I said, for the triangle, because you actually, for the linear triangle, because you actually have shape functions in terms of x, y, let's say that you have some random triangle, just like I was saying in the homework. You have some random triangle with some x1, x2, and x3 coordinates, then you can actually compute, well, I don't have off the top of my head, I don't remember what this function looks like, but it's some ugly function in terms of X and Y. And it depends on the nodal coordinates. But there is some function, it's in the notes for this and for the other functions. And then you can take that function and get the gradient. And I also don't remember what the gradient looks like. It's a vector because you need to take the derivative with respect to X. I think this is something like Y2 minus Y1 plus something like that. I really don't remember. And this is something like X2 minus X1. There's a combination of these. I don't know if you multiply at this multiply. Well, I really don't remember. It has combinations of differences between the Y coordinates, and the other one has combinations of the difference between the X coordinates. We'll actually compute it on Friday. But the main thing that I want to point out is that there is some function that you can go look at the notes and write down. And if you can take the derivative of that function, you will get the vector, the gradient vector, which are derivatives with respect to X and Y. And importantly, this vector is constant because this is a linear function. This is a constant vector, which means that after you plug in the values of the nodal coordinates, you will get some number. After you plug in what the coordinates of the element are, you will get some number, I don't know, 2,3. Similarly, for the gradient of the second shape function, again, you can start with the definition of the shape function. You can take the derivative and you'll get some expression that will not have X or Y. It will only have, when you do that, here you will no longer have X or Y, you will have only combinations of the, I mean, this is obviously incorrect, but it has combinations of the nodal values. It does not have X or Y. So that means that when you plug in the nodal coordinates, again, you will get some number. Or some vector, I guess. Oh no. And similarly for N3, right? So you're gonna end up with some vector. So what that means is that when you put that into the stiffness matrix, then you're gonna end up with integrals over the triangle of the K, which is just a number, times the different vectors. Like in this case is 2, 3 dotted with 2, 3. I should keep on using the square brackets. And then integral over the triangle of k, which again is just a number of 2, 3, not 2 over 3, but just 2, 3, dotted with minus 1, 3. And so on. Now, because all of these are just numbers, when you dot the vector 2, 3 with 2, 3, that is, for example, just 4 plus 9. So 13. For the first one is just 13k, right? So that one you can take out of the integral. So if you actually do the dot product, this one is, for example, 13k, and the k is, again, just a number, so you can take that out of the integral. And then we're left with integrals that will look like this. So then again, k, and the other one is minus 2 plus 9, so 7. Integral 7k, integral over the triangle, over the a, and so on. And so for the linear triangle, actually, the integrals are trivial. What are these integrals? Anybody except Thomas? I already told you. So what is this integral? If I have nothing, yes. Just the area of the triangle. So these are, so this is just the area of the triangle, 7k times the area of the triangle, and so on. So for the linear triangular element, actually the integrals are trivial because everything is a constant. You take everything out of the integral, and then the integral of dA is just the area. So for the linear triangle, it should look very, very simple. For the case of shape functions in terms of psi eta, for example, or for the quadrilateral elements, unfortunately, that is not that simple. So I will try to do a little bit of that on Friday. But the main idea is that we have to use Gauss quadrature. So at the end of the day, what will we do? Yes, I know. What will we do if we have an integral for which we cannot just simplify to get a constant? Then we'll just do Gauss quadrature. What will that entail? Exactly the same that you did for in the quiz, for example. I don't know if you did it for the homework 3, because I think for homework 3, you could also just use shape functions with respect to x, if I remember correctly. So you actually didn't have to do Gauss quadrature, did you? I don't remember. I mean, I had one problem that was just Gauss quadrature, but I don't know if I made you solve an entire FE problem with Gauss quadrature. But what you would do is you would just follow the table to where to evaluate, and then you would just evaluate the gradients of the shape functions at those points, and then just add up with the corresponding weight. I'll do that on Friday. But yeah, there's no option but to do Gauss quadrature if you have, for example, quadrilaterals. Any questions? All right, so for force vector, that one is the other integral that we have. Let me just copy that one. I am so nervous because this is gonna run out of battery. Please don't. All right, so we have this one. And again, what we're gonna do is we're gonna take out the sum and take out the nodal values. So just some algebra, we're gonna have this integral over the element of NIS. This looks exactly the same as in the 1D case, right? So just the vector with the nodal values and then the integral of Ni times the source term. The only thing that is different is that the shape functions are 2D shape functions, so the integral are double integrals, but this looks exactly the same as in the 1D case. This is again a vector with the nodal values. So for the triangle, that would be 3. And this vector right here is just an integral over the element of n1 times s, integral of the element of n2 times s, integral over the element of n3 times s. And this is the force vector corresponding to that source term. So again, this looks exactly the same as the 1D case. What is different? Well, the difference is that these integrals are over the triangle, whereas in the 1D case, these integrals were over the piece of line. Now, how you compute those integrals? Again, I'll tell you for the linear triangle, because that one is not too bad. So here, we're gonna make a big assumption. So assume S is constant. This is not necessarily the case. The source term could be a function of X and Y. But let's assume that S is constant. So if S is constant, then the force vector is the integral over the triangle of S, which is a constant again, times N1. So because S is a constant, I'm gonna take it outside of the integral. So what this means is that when S is a constant, I can take it outside of the integral. So the only thing that I need to integrate is the shape functions over the triangle. And any guess as to what those integrals are? Without actually computing the integral. Obviously, you can write out what the first shape function is some function of X and Y. You can set up your double integral. But you can get the answer without actually doing anything, just by some geometry. To that, let me illustrate what the first, let's say you have some arbitrary triangle. Of course, you could write, and this you can do for your homework, you can write the first shape functions in terms of, the first shape function in terms of xy is gonna be some ugly expression, right? And then to set up the integral, you would have to then try to split the integral, for example, between this x and this x, and between these two lines, and then between this x and this x, and between these two lines. That is a little bit complicated, but you can do it. What is the alternative? What is the first shape function look like? Let's assume that this is the first node. So the first shape function is this little plane that goes from 1 to 0. Geometrically, what do we do when we integrate a function over some area? You are finding the volume of that. Yeah. So in 1D, when you integrate a function, you are getting the area under the function. When you have double integrals, when you integrate a function, what you are getting is the volume of that. So what is the volume of the pyramid that is defined by this plane that is 1 at the first node and goes to 0 at the other nodes? You can look that up, but I'm not gonna write it here, but it's the volume of a pyramid. There's a simple formula for that. It has height 1, right? And it goes to 0 at the other ones. So just formula for volume of pyramid. And actually, they are all the same. In that the volume of this pyramid that has 1 at node 1 and goes to 0 at the other ones, and the volume of the other pyramids, they are all the same. So for the case of the triangular element with the linear shape functions and the constant source term, which is what you have in your homework, then you can do the integral, actually set up the double integral, or you can just calculate the volume of that pyramid. And it should be the same. For quadrilaterals or other like higher order elements, quadratic elements, then you can't, you have to do Gauss quadrature. So you just have to go to the table, see where you need to evaluate, and evaluate at those points and add with the weight. Questions? All right, so we have the stiffness matrix. I'm gonna skip that. I'm gonna skip that, skip that. I got 8% living on the edge here. Let's talk assembly. So at least for the linear triangular element, you can see how you can get the stiffness matrix and the force vector. I have been ignoring the flux force vector. And then the next thing is the same thing that we were doing for the 1D case is we need to do assembly. What do I mean by assembly? Same as before. So let's say that for some element, say this is some element, and we know from the mesh, we know, let's say this is element 3, and element 3 is made out of the nodes, I don't know, 4, 7, and 16. That information that the element 3 is made out of nodes 4, 7, and 16, that should be in your array that is the element array. So that information is in the element array. Because remember that the element array has the element, and then it has the 3 nodes that make up this element. So here in this array, there's a line, the third line should have 4, 7, 16. And this is what we are going to use to do the assembly. So for this element, we are gonna get the K of this element is gonna be this 3 by 3 matrix, right? And we want to put that into a big K matrix that is n node by n node. So the big stiffness matrix is n node by n node. The small element stiffness matrix is 3 by 3. How do we decide where to put things? So this one, as usual, we're just gonna write the node numbers corresponding to from the element array. So 4, 7, 16, 4, 7, 16. This is very similar to what we do in 1D. So here there's all of them. So 1, 2, 3, blah, blah, blah. Actually 4 is there, right? 4, then at some point there's a 7, and at some point there's a 16, and then maybe it goes to, I don't know, 50. 1, 2, 3, 4, 7, 16, 50. So the big K matrix has all the nodes in the rows and columns. The small stiffness matrix is always 3 by 3. And then for this particular element, what we should write is 4, 7, and 16, because that is the information that we have from the from the connectivity array. And this tells us that, for example, the first entry should go to the 4-4 entry, right? Then this entry right here should go to the, well, both of these because they are symmetric, the 4-7 and 7-4, right? So the one in the middle right here, which is the 7-7, should go to the 7-7. Then these two, which are 4-16, should go to the 4-16. These are the 7-16, so 16 times 7, 16 times 7, and then the last one is the 16-16, which is right here. So the process is very much the same as in, I know, very much the same as in the 1D case. So just write the global known numbers in the rows and columns, and then for the big K, that one has all the numbers, and basically just find the corresponding entry. So the same idea as in 1D. For the force vector, you can imagine is the same. So this force vector for the element, and then we write 4-7-16. And then there's the big force vector. And that one has all the numbers. And then, you know, this goes to here. This goes to here. This goes to here. So the assembly is basically the same idea as we already did in 1D. Questions? All right, so let's wrap it up with the, so once you do the assembly, then you actually get a system of equations. So if you do the assembly, you're gonna get a vector of W's with all the W's from 1 to however many there are, like 50, for example. This is size and node. And then that one times the big K matrix times the T vector. Again, this one has all the nodal values. And then I'm passing let me go back to the weak form that I had over here. Where is it? I'm gonna pass this to the left and also the flux vector. This one, I still haven't told you what this one is. So, but I'm gonna put them here. So here, minus, there's a force vector from the sources. That one you know how to assemble. And then finally, there is a force vector from the fluxes that I haven't told you how to assemble. And you also need reactions that I also haven't told you, but they are. So this equals the zero vector. This equals just 0. Now this has to be true for all W's with only one condition, right? With the W's at the boundary with essential. So there are some nodes for which we know the temperature. For those nodes, we don't know the reactions. I'll mark them in red. So there's, well, actually I'll mark them in green. So there are some nodes for which we know the temperature, right? So let's say that these nodes are, there's some nodes here for which we know the temperature. And depending on how you arrange your mesh, you can name your nodes such that the first few nodes are the ones with known temperature. So they all appear at the beginning. That depends on how you number your mesh. For those nodes, we don't know the reaction, right? So for those nodes, we don't know the reactions. This is the same as in the 1D case, right? So any node for which you have an essential boundary condition, you don't know the nodes with essential boundary condition unknown reaction. So that R vector is just, it will have unknown reactions for those nodes. Other than that, it will be 0. But for those nodes, we know that the W is 0, so the equation is still satisfied. And then there's a bunch of internal nodes, and then there's some nodes with flux boundary condition. Let me use purple for that. So there's some nodes, and these, they don't matter where they appear. But there's gonna be some nodes that will have a known flux. So for those, we need to add the flux. So this is, we will put the corresponding Q. My God, I'm playing with fire here. Add flux Q bar to nodes with natural boundary condition. The rest are 0, right? So the rest here, this is just like in the 1D case, right? So only need to identify which nodes are in the boundary with a flux boundary condition, and then you will need to add the flux to those nodes. Oh, it's 10:20. Wow, you made it. So that's it. So the solution is solve this system. Because this has to be true for all W's, then you can say it doesn't matter what the W is. All you need is this. So all you need is solve this system of equations. For the vector T. Solve for, I mean, technically you would say solve for T and solve for the reactions. Right, because what are the unknowns in this problem? The unknowns are all the temperatures, right? All those orange temperatures, those are the unknowns. And the reactions for the nodes for which we know the temperature. So that's it, that's the problem. No questions. I'll see you on Friday. I made it. Well, the iPad made it.